Hello all, welcome to this course on time series modeling and forecasting using R. Okay. Now again this is the last session for this week, obviously the theoretical session, and of course in the next session it will be a practical session in R. So again just to quickly summarize to where we stand before we discuss anything new in this session. So this entire week has been devoted to exploring how do you model changing variance of a time series, or rather how do you apply some volatility modeling. Okay. And again volatility means changing variance. So let us say again just to give you a very simple example is that if you assume a stock price and the stock price behaves like this initially, but due to some unforeseen news you see lots of fluctuations in between, and again you have lot of activity down the line. So we will say that if you observe the overall variance of this plotted data, or rather plotted return series, then you can see some changing variance in that. Okay. So rather than only focusing on describing the mean of the model, which we have been doing so far using ARMA models or ARIMA models, SARIMA models, etc., but rather than only doing that, can you also try to model the volatility in the underlying time series, or can you try to model the changing variance of the underlying time series. Okay. And in this period we have been exploring or talking about different sort of models. The first model we talked about in couple of sessions back was the ARCH model, which stands for autoregressive conditional heteroscedasticity, and then heteroscedasticity stands for changing variance. And just in the last session we extended the ARCH model, because again we have seen that ARCH model may not be very wholesome sort of a model in different situations. So the extension was coined as GARCH, and then the full form of GARCH is generalized ARCH, or generalized autoregressive conditional heteroscedasticity. Okay. And again we saw some limitations of GARCH in the last session, some key features of the GARCH model in the last session, then how do you fix the optimal orders, right. So all these were a few things we have seen in the last session. And right towards the end, or somewhere in the middle of the last session, I mentioned that in the next session, which is this one, we will talk about some other extensions of the GARCH model as well. Because what happens is, so a simple GARCH model may not be able to capture the asymmetry. So if you remember, I am not sure how many of you remember, if you do not remember, you might have to go and again rewatch the previous sessions, but again the GARCH model, or rather let us say a simple ARCH model or GARCH model, is not able to capture the asymmetries in the underlying practical data. Now firstly, what do you mean by asymmetries? Asymmetries mean that if you have a negative shock or some negative news, so a negative news has a much more drastic impact than a positive news. Okay. And of course this is very widely seen in, let us say, stock markets as well, right. So if a company declares some positive news, then the market may not be, let us say, up by a whole lot, right. So market may move up by, let us say, 5%, 10% at the max. But if some negative shock comes or some negative news comes pertaining to some company, then again we have very well seen again in the past is that the price has a tendency of dropping, let us say, quite a lot. So let us say 10%, 15%, 20%, right, which means that a negative news or rather a negative shock can create a much more turbulence than some positive event or a positive news. Okay. So for all such ideas, a simple ARCH model or simple GARCH model may not do the job. So we have to study some extensions of a standard GARCH model. Okay. Okay. So we will study all these extensions one by one in detail, do not worry. But then firstly a brief background as to why we have to study the extensions again. So specific variants of a GARCH model exist in literature tailored to capture different characteristics in the underlying time series data. Okay. So each and every different practical time series data is not the same, of course. So how do you tailor to capture the different characteristics in all these different sort of time series data? Of course one can't put forward a simple GARCH model for each and every one of that, right. So one would require some specific variants of the GARCH model as well, particularly volatility dynamics in financial and economic context. So a few examples are these. So GJR GARCH, and then we will talk about exponential GARCH, then we will talk about threshold GARCH, then the next one we will talk about is asymmetric power GARCH, then fractionally integrated GARCH, multivariate GARCH, and lastly non-linear GARCH. And of course if you find the literature, one can actually see a lot of other extensions as well, but all those extensions kind of stem from one of these that I have listed here. Okay. So predominantly these are the important ones. So GJR GARCH, E GARCH, threshold GARCH, asymmetric power GARCH, etc. Okay, so during the course of this entire session over the next few minutes, we will talk about each and every extension which is listed here in a bit more detail along with some example corresponding to each of the extension. Okay, so now the very first one is GJR Garch, right. So, GJR Garch, the full form is Gloston, Jagannathan and Rankal Garch. So, by the way, GJR stands for the acronyms of three people. So, Gloston, Jagannathan and Rankal who put forward this model. Okay. So, in short GJR Garch. So, what is the property here? So, GJR Garch captures the asymmetric effects in volatility, right. So, as discussed before that a simple Garch model fails to capture the asymmetries, but GJR Garch captures the asymmetric effects in the underlying changing variance, where again just to summarize that negative shocks or bad news affect volatility differently than positive shocks or good news. So, how can you sort of capture the asymmetry? So, using this equation. So, the model definition is as follows. So, sigma t square equals omega, omega is as same as before. So, omega is the intercept or the constant term plus alpha into epsilon t minus 1 square. So, epsilon t minus 1 square is the squared residual plus gamma into epsilon t minus 1 square, but this is the extra bit here. So, what we are doing is we are putting an indicator function. Okay. So, again I am not sure how many of you are familiar with the indicator function notation. So, again indicator function is not a very difficult thing to sort of analyze. So, I will give you a small example which is outside of time series. So, let us say if I write down capital I of a random variable x being let us say less than 0, okay. So, let us say x is the random variable. So, for a second come out of a time series literature. So, this is a very general sort of a random variable in a stats literature. Okay. So, if I have this particular indicator function that capital I x is less than 0, so this would take two values. So, it would take one value of 1 whenever this event happens, which means whenever x is less than 0, otherwise it will take a value of 0. Okay. So, any indicator function can only take two values, either 1 or 0, and then when would it take a value of 1? Whenever this underlying event happens, and otherwise it will take a value of 0. Similarly, coming back to this equation. So, now if you want you can pause the video and then try to answer the question as to when would this indicator function take a value 1 and when would it take a value 0. Okay. So, simply put, so this indicator function would take a value 1 whenever this residual epsilon t minus 1 is less than 0 and otherwise will take a value 0. So, I will say that this is the extra part which was not seen in the Garch model, right. So, again omega plus alpha epsilon t minus 1 square plus gamma epsilon t minus 1 square, but you have some restriction here that the residual should be negative plus beta into sigma t minus 1 square. Okay. So, again one important point is that if you observe the order in the model, so order in the model is nothing but 1 1. Can you see that? Because you do not have summations anywhere. Okay. So, just as a simplicity I have tried to ignore the summation signs. So, and then I fixed the orders to be 1 1, but of course, if you want to extend this further to multiple orders, I can involve let us say something like alpha I or gamma i's or beta i's, etc., but of course, there will be summations there. Hopefully, this point is clear that rather than making the overall equation difficult looking, I have restricted myself to fix the orders to be 1 1 wherever possible. Alright. Okay. So, again just to summarize quickly that this is the GJR Garch model, and this is exactly what we talked about a short while back, that the indicator function epsilon t minus 1 being negative is an indicator function equal to 1 if the previous residual is negative and 0 otherwise. And what exactly is gamma? So, gamma, which is assumed to be positive, captures the impact of negative shocks, right. So, if the past residual is negative, which would correspond to a negative shock, this is the coefficient that captures the impact of that negative shock. Now, lastly, what exactly could be an application? So, financial markets where bad news tends to increase the volatility more than good news, for example, leverage effect. Okay. Now, again this is a very similar kind of an application we have been seeing throughout this week, right. So, the leverage effect means that whenever a bad news tends to increase the changing variance more than good news. Okay. Alright. So, the first model is GJR Garch. Now, coming to the second model. So, second model is called as E-Garch. Okay. So, E-Garch or rather the exponential Garch. So, E-Garch means exponential Garch. So, E-Garch handles the leverage effects again. So, again if you see briefly both in GJR Garch or E-Garch or some of the other extensions study today, So, the common idea is how does each of the extension tends to handle the asymmetries. Okay. So, again eGauge handles the leverage effects and ensures that the conditional variance is always positive without requiring non-negativity constraints on the parameter. So, there is one thing extra here, that the eGauge sort of assumes that the conditional variance is always positive without requiring any non-negativity constraints on the parameters. Okay. And this is the model definition. So, log of sigma t square. So, rather than simply putting sigma t square, I am taking log of sigma t square, again equal to some slightly advanced looking equation. So, it starts with omega again. So, omega is the constant plus beta into log of sigma t minus 1 square. Again, this is a small change here as compared to Garch model or GGR Garch, etc., that we are taking a log on the past lag of the conditional variance as well, plus alpha into this ratio. So, this ratio is completely new. So, ratio of what? So, ratio of epsilon t minus 1 divided by sigma t minus 1, and then plus the last coefficient is gamma multiplied by again the absolute value of epsilon t minus 1 by sigma t minus 1 minus its expected value. Okay. So, again I will not spend time into describing the nature of the equation, because the nature of the equation is not very easy to understand, but again the whole point is that a couple of important points to note here. So, firstly again eGauge is capable of handling asymmetries or leverage effects, and the second point is eGauge ensures that the conditional variance is always positive, which is an advantage of course, right, because otherwise we would have required some non-negativity constraints on the parameters, stuff like that. Okay. But eGauge does not require any of those things, because it sort of ensures that the conditional variance is always positive. Okay. And how is it doing that? By taking logs. So, the logarithmic transformation ensures positivity of the conditional variance term, which is sigma t square, while gamma assumed to be positive captures the impact of negative shocks as before. Okay. So, this gamma stays the same. So, again gamma has a tendency of capturing the impact of the negative shocks, while since you are taking a logarithmic transformation of sigma t square is ensuring the positivity of the conditional variance term, which is sigma t square. And lastly, the application part. So, again financial assets with pronounced leverage effects such as equity indices, etc. Okay. So, rather I can actually try to put forward an eGauge model or a GGR Garch model, and then down the line we can compare. So, which model suits the underlying data better. Okay. Okay. Now, the third one is called as threshold Garch. So, again a small disclaimer that the short form is T-Garch, full form is threshold Garch, and T-Garch is similar to GGR Garch, different only as it involves a standard deviation term in place of the variance. So, we will see exactly how. Okay. So, this is the model definition. Again just to summarize that T-Garch is not different widely from GGR Garch. The only difference is in GGR Garch we are exploring about epsilon t minus 1 square, while when it comes to the threshold Garch we are taking the standard deviation term in terms of epsilon t minus 1 without the square. So, we will see what I am saying. Okay. So, this is the model definition. Again how do you write down the equation? So, on the left hand side we are trying to model the conditional variance as always, which is sigma t square, and then sigma t square equals omega plus alpha into absolute value of epsilon t minus 1 plus gamma into epsilon t minus 1 indicator function, again the same thing. So, epsilon t minus 1 is negative plus beta into sigma t minus 1 square. Okay. So, this is the model definition, right. Again just to summarize very quickly, that instead of epsilon t minus 1 square, let us say here or rather there, we are taking the standard deviation. So, this is the only difference between GGR Garch and T-Garch. Again when it comes to application, again from a financial markets point of view, that financial markets where extreme negative shocks disproportionately affect the volatility. Okay. So, as you see broadly speaking, the T-Garch, E-Garch or GGR Garch, they revolve again around the idea of capturing the asymmetry, which is also called as leverage effect, etc. Okay. Now, the next one is called as AP arch, right. So, AP arch, the full form is asymmetric power arch, right. So, AP arch or asymmetric power arch captures asymmetry and allows for flexible modeling of power transformations of the volatility. So, exactly how? So, this is the model definition. So, I guess the name itself speaks as to where would be the power, right. So, again asymmetric power arch. So, initially rather than taking sigma t square, we will upfront take sigma t to some power delta. So, sigma t to the power delta again equal to the constant term omega plus epsilon t minus 1 absolute value of that minus gamma into epsilon t minus 1 to the power delta attached to the coefficient alpha. Okay. So, again all the coefficients are as we saw earlier as well. So, alpha, beta, gamma, etc. The only difference is how do you put forward the lagged residual term and the lagged conditional variance term. So, whether you take variance, whether you take standard deviation, whether you raise it to some power, whether you take absolute value. So, these are some small differences that all these extensions have. Right. For example, again just to summarize, so sigma t to some power delta equals omega plus alpha into absolute value of the standard deviation, which is epsilon t minus 1 minus gamma into epsilon t minus 1 to the power of delta plus beta into sigma t minus 1 to the power of delta, where delta is nothing but the power parameter which determines the transformation of conditional volatility, while gamma is the asymmetry parameter. So, gamma is the asymmetry parameter while delta captures the power parameter. Okay. Again, what is the application? So, markets with non-linear and asymmetric volatility patterns such as energy or commodity markets. So, these are some of the applications where an AP arch model seems suitable. Okay, now the next one is slightly different. It is called as fractionally integrated gauge, or in short FI gauge or Phi gauge. Okay. So, Phi gauge or fractionally integrated gauge, and the idea here is slightly different as discussed a short while back, that Phi gauge tries to model the long memory property in the underlying volatility. So, rather than capturing the asymmetry, it tries for capturing a slightly different thing, which is long memory. Okay. And again long memory, again as discussed before, almost all of you must know as to what you mean by long memory. So, long memory means that if a time series sort of reverts back to its mean very slowly in the long term, then we will say that time series has some persistence down the line, or it sort of captures some long memory properties. Okay. So, again in short, this Phi gauge models the long memory in the volatility, capturing persistence which decays very slowly over time. And this is exactly how it is capable of doing it. So, the model definition combines fractional integration with gauge dynamics. So, it is a combination of two things. So, fractional integration and some gauge dynamics. Okay. So, again if you vaguely remember, right. So, again if you do, then it is a very good thing for me at least, that again if you vaguely remember the idea of how did we write down the fractionally integrated models, and this is exactly one way of writing it down. If you look at the left hand side of this equation, so there has to be some coefficient. So, phi L 1 minus L to the power d applied on sigma t square. So, this is the operator which is applied on sigma t square. Of course, phi of L is the set of coefficients, and 1 minus L to the power d is the operator applied on the conditional variance, equal to sort of a similar thing. So, omega plus 1 minus set of coefficients beta L into epsilon t square. Okay, where this 1 minus L to the power d is a fractional differencing operator with d assumed to be strictly between 0 and 1. Okay. So, again just to summarize quickly, that this Phi gauge is nothing but a combination of some fractional integration with the underlying gauge dynamics. Okay. And again when it comes to application point of view, so one can see application again in financial markets where long term persistence in volatility exists, such as bond yields or exchange rates, etc. Okay. So, if you want to counter two things, so long memory or persistence along with trying to model the gauge dynamics, then probably Phi gauge would be much more suitable. Okay. Alright, now the next one is M gauge. So, M gauge stands for multivariate gauge, right. So, M gauge as the name suggests is called as multivariate gauge, which extends the gauge to multiple time series, capturing the co-movements in the volatilities, right. So, let us say if you have more than one time series to capture, right. So, let us say if you have 2 time series to capture or 3 time series to capture. So, in that case a simple gauge model will not do the job, right, because gauge model is univariate. So, you have to shift attention to some bivariate sort of a model or multivariate sort of a model, and then in this regard a M gauge model or multivariate arch model extends the gauge to multiple time series, capturing the co-movements in volatilities. And these are some of the popular specifications or some popular models under the M gauge framework. So, the first one is VECH model. So, what it does is directly models the variance covariance matrix, but suffers from over parameterization. So, by the way, these three are models under the M-Garch model. So, again we will not go into detail. So, I just thought of putting a slight variant of univariate Garch which is called as M-Garch. So, second model could be BEKK model. So, imposes structure on the variance covariance matrix for more parsimonious modeling. And lastly, DCC Garch or dynamic conditional correlation Garch. So, models time varying correlations alongside volatilities. So, the last one could be seen very often when it comes to, let us say, the actual application point of view. So, the DCC Garch called as the dynamic conditional correlation Garch, and what it does is it sort of models two things. So, the time varying correlations as well as the volatilities. And then lastly, N-Garch. So, N-Garch stands for non-linear Garch, which introduces non-linearity to capture more complex dynamics in volatility. And this is exactly what the model definition looks like. So, combines the fractional integration with Garch dynamics, right. So, again let us say sigma t square equals omega plus alpha epsilon t minus 1 square plus beta sigma t minus 1 square plus lambda epsilon t minus 1 into sigma t minus 1. So, I guess there is a small typo here. So, you should erase this line because this has nothing to do with fractional integration. Okay. So, completely ignore that line. So, the model definition, so the model definition is correct, but the description is not correct. Okay. So, non-linear Garch, the whole idea is that how do you capture the non-linearity in the underlying dynamics of volatility. And here can you see that how is this capable of capturing the non-linearity? By this multiplication term. So, what you are doing is you are multiplying both the things. So, the past residual as well as the past conditional variance to involve some complex dynamics in changing variance. Okay. And this is the attached parameter to do that. So, lambda is a parameter to capture the non-linear interactions. So, we are having some interaction between the residual portion and the variance portion. Okay. And the application point of view, so high frequency financial data with complex volatility behavior. So, this is one application of N-Garch. Okay. And then you could have one more extension called as H-Arch. So, H-Arch is called as heterogeneous arch, which explains volatility using returns aggregated over multiple time horizons. So, again a slightly different kind of an idea. So, this is the model definition. Again you can ignore this line, it has nothing to do with fractional integration, but this is the model definition. So, sigma t square equals omega plus summation k going from 1 to capital K alpha k into 1 by k summation I going from 1 to k epsilon t minus 1 square. So, the whole idea behind H-Arch is that the H-Arch is capable of explaining volatility using returns aggregated over multiple time horizons. So, captures the idea that market participants operate over heterogeneous time scales. Okay. So, let us say if you do not have some similar time scales, if you have heterogeneous time scales, then what sort of a model is suitable in capturing that idea, right. So, one example is H-Arch, and again the application of that could be seen in high frequency trading and markets with participants reacting to news over different horizons. And then this last slide is sort of tells you the summary of all the applications. So, let us say GJR Garch or T-Garch, their application could be equity markets where leverage effects is seen, right. Then exponential Garch, let us say stock indices or currencies with strong asymmetry in volatility response, or AP-Arch, let us say commodity and energy markets with flexible volatility dynamics, or Phi-Garch where you can see some long memory in bond yields or currency volatility, etc. And lastly, M-Garch, which could be seen applications in portfolio risk management or studying the inter-asset relationships. Okay. So, this is the only one which is different in the sense that this extends from one time series to multiple time series, and hence the name multiple or rather multivariate Garch, or in short M-Garch. Okay. So, I try to put this which is slightly different because it is termed as E-Garch X or Garch X, which extends Garch by incorporating some extra variables in that, and these extra variables are called as exogenous variables, which are XT. Okay. And how exactly? So, let us say XT is some extra independent variable. Okay. So, let us say you create some time series, you have some univariate time series running along, and on top of that you have some extra variable which sort of affects the time series as well. So, one can use E-Garch X model for that. Okay. Again you can erase this line, right. So, this is the model definition. So, sigma t square equals omega plus the same summation in terms of epsilon t minus 1 t minus I square and this is the extra term which is attached to the conditional variance, which is xt. So, what exactly is xt? So, xt is the exogenous covariate affecting the changing variance. Okay. And then application could be modeling volatility with macroeconomic indicators, news sentiments or financial stress indices. Alright, so very lastly we will discuss one very important extension, another important extension which is called as ARMA plus Garch model. Okay. So, what one can have is one can have a combination of ARMA plus a Garch model. So, an ARMA plus Garch model combines the strength of an autoregressive moving average, or in short ARMA model, for modeling the mean of a time series, with a Garch model for modeling its conditional variance or volatility. This hybrid approach captures two things. So, serial correlation via the mean model, which is ARMA, and time varying volatility via the Garch structure. Okay. So, this is a combination of two things. So, ARMA plus Garch. And how exactly? So, again both the equations would be pretty straightforward. So, this is exactly how the ARMA equation runs like. This is nothing but the usual ARMA PQ model, right. So, yt equals mu plus the AR part plus the MA part plus the random error, and when it comes to capturing the variance, we can capture the variance using a Garch RS model, right, using this structure. So, sigma t square equals omega plus the arch term plus the Garch term. Make sense? So, this is a two level model. So, you are trying to capture the mean using ARMA, extracting the residuals from the ARMA equation and then trying to incorporate those residuals in the changing variance structure. Okay. And lastly, we have this last slide capturing some applications. So, the first application will be seen in finance, let us say modeling stock returns with serial correlation and volatility clustering. Second could be seen again in finance, which is forecasting risk metrics such as let us say VAR or value at risk, or one can see in macroeconomics, let us say modeling GDP growth or inflation with time varying uncertainty, or in energy markets where let us say one focuses on capturing volatility in commodity prices like oil or electricity. So, all these could be applications of ARMA plus Garch sort of a setting. Okay. So, with this we come to an end of this entire umbrella of modeling volatility and modeling changing variance using different sort of extensions of Garch, ARCH, eGarch, GGR Garch, etc. Right. So, I think this particular week we sort of witnessed lots and lots of models, right. So, all the extensions of Garch, we started with ARCH, then the actual Garch, then Garch 1.1 or Garch PQ, and all the extensions we have seen in this lecture. Okay. Now, in the next lecture we will pay attention to a practical example where we will tie all the things down by using some simulated data and a practical data. Okay. Thank you.